I'm very excited about Pei's work. He's been working on AI for 2 decades or more, and he's one of the very few people that continue to impress me with his ideas. So please welcome Pei.
Thanks for coming, and it's a great pleasure for me to here to present my work. As you can see from the title, it's about cognitive logic versus mathematical logic, and the way to artificial general intelligence. Okay, I assume here most people are familiar with the phrase artificial intelligence, but you're probably not familiar with what is called artificial general intelligence. Which is an emerging subfield of artificial intelligence, or AI, which is currently still quite a small community. And what makes it different from the rest of AI, which according to my summary is the following points. One is the belief that it's actually possible to actually build a thinking machine, or a machine intelligence, which is comparable to human intelligence in all major aspects. Also, second is the belief that intelligence is actually a single general purpose capability rather than a collection of domain-specific capabilities. And finally is the belief that intelligence should be addressed as a whole rather than piece by piece. So, well, then people say, how to do it? Okay, that sounds good. Okay, how to actually do it? Well, clearly there's, at the current moment, there's still many different opinions. Okay. So here I can only cover one approach which I have been following, which starts from the concept of logic. Well, intelligence have different understandings. One of them is to understand intelligence is some kind of rationality or validity, or the ability to always do the right thing or the best thing, yeah, in some sense, of course. Then, on the other hand, it's easy to realize, this is also have a large overlap with the concept of logic, which is the study on valid reasoning, which have been going on for thousands of years. So, clearly, there is a possibility of build an AI or AGI, whatever you call it, by building a reasoning system that following some kind of logic, at least to use this as a major piece of this AI. So for logic, we already have a lot of theory out there, usually collected under the title of mathematical logic. Especially here, I assume most of people are familiar with, say, fourth-order predicate calculus, which specifies a formal language to represent your knowledge and inference rules to derive new knowledge from given knowledge. And also, there's something called model theory, which specifies the semantics of the language and the rules, okay? Which basically say that what you describe in your system are just names of the real thing in the world, okay? And whether your sentence is true or not depends on whether they match the reality or not, okay? With a whole bunch of technical details, but that's the basic idea. Then what? Then to actually build such a system in a computer, you also need some kind of memory structure, which is usually organized according to some database theory or knowledge-based theory, which can support, say, store some information and retrieve from the memory. And finally, there how to control the process. Well, that's typically from the theory of computability and computational complexity, and the theory about algorithm, right? You have a procedure, you follow that, you solve the problem. So that's kind of like the traditional theory, where I roughly call them, say, mathematical logic. Okay? So that's a whole bunch of theory that have been there, have proved themselves in many domains. They have solved many theoretical and practical problems. However, when those bunch of theories are applied to artificial intelligence, there are all kinds of trouble that arise. Okay? There are so many trouble to the extent that I don't really have the time to explain each of them one by one. So instead, I put them into clusters, groups, okay? So the first group are all kinds of uncertainties. It's very easy to recognize that because if you think about your self-thinking process, you compare that with the requirement of logic, you'll see they doesn't match at all. Okay? According to logic, everything should be certain. But in reality, everything is messy. Okay? So here I mentioned a couple of them. So that's one major obvious difference between the reality of human thinking and what mathematical logic requires. And another group of problem is traditional logic or mathematical logic, as I mentioned, typically handle binary deduction, which roughly speaking is from given truths to derive new truths, from truths to truths. But actual human thinking is more complicated than that. Especially it have a whole bunch of what we typically call non-deductive inference, like induction, abduction, analogy, and so on. Okay. Again, here I'm not going to talk about the technical definition or detail. It's basically what makes them different from traditional deduction is they cannot guarantee the truth of the conclusion, even though you start from the truth as a premise. It's kind of like this a way to make guesses, to produce hypotheses, to kind of jump into conclusion for which you don't really have a solid ground. Okay? So according to traditional logic, all those things are bad. But on the other hand, we all know that we depend on them on a daily basis. Okay? So if you want to build a logic-based AI, you will have to explain all those kind of things. Okay? So that's another group. And a third group is all kinds of paradox or problem and so on. Each of them has a long story behind them, and I guess you may be able to recognize some of the names. So in summary, what they show us is, according to logic, you're supposed to do this. Okay? But if you check human reasoning, in reality, everyone else, almost everyone, maybe except the logicians, okay, they will do something else, which according to logic is completely wrong. But we have a lot of evidence showing that people are actually doing that. So who is wrong in this scenario? Many people say, well, humans are just irrational. We know us. Okay, we are not that good. So if you really want to build AI, you don't want to follow human bad example, you want to follow logic, that's a good example. But on the other hand, there are also people who think actually something's wrong here in logic itself, because it's supposed to capture reliable, stable human, the patterns in human, actual human thinking. But those problems shows that's not the case. Okay. So anyway, we need to explain them. And finally, the group is about computability and complexity. We know that according to logic, many problems, there is a perfect solution. Meaning that you just try all possibilities, then you pick the best answer, then that's by definition the optimal. But in reality, we know that everyone, at least in computer science, know that's impossible. You don't have the time and space. Okay? You have combinatorial explosion and all kinds of other issues. So you either don't have an algorithm, or you have an algorithm, but it takes too long to finish. So it's just basically the same thing as you don't have it. Okay? But it seems the human mind is able to work in that situation. But the computer, so far, still cannot. Okay? So all those problems, none of them is discovered by me. Okay? All of them are well known to the field for many years. Actually, many of them are known before the concept of AI was formed. Okay? They have been studied in logic, in philosophy, in psychology, in many other fields. Now, all of those problems come into AI because you guys said you can build a thinking machine. Okay? Now they all become our problem. So no surprise that there has been, again, a long list of proposed solutions. Again, I'm sure each of you can recognize some of the items I have in the list. We don't have the time to discuss one by one. And this is by far from a complete list. But there is one thing to me in common. That is, each of the solutions is typically proposed to one or a couple of problems in my previous problem list. Okay. So people here are using a good strategy or heuristic that have been used in computer science from the beginning, that is divide and conquer. Okay. Intelligence, too complicated. Okay. Again, use logic for actual thinking, that's too complicated. We identify one of the problems. We try to solve that one. Okay. Then hopefully, maybe after that, we can solve others, or some other people can solve the others. Then eventually, we have a complete solution for those things. And now I can begin to talk about my research. The biggest difference of my approach is to try to identify a common root, or at least to me, there seems to be a common problem behind all the issues I mentioned before, or most of them. That is, if you think about it, as the name suggests, mathematical logic and all the related theories I mentioned before were developed in the study of what mathematics, of course. Okay? Concretely speaking, they're developed in the study of the logical foundation of mathematics. But on the other hand, if you check the problem list, almost all of them appear outside mathematics, or traditional or classical mathematics. For example, fuzzy logic, well, in mathematics, you're not allowed to define a fuzzy concept in the first place. But as soon as you go to natural language or human thinking, you'll see every concept is ill-defined, it's fuzzy. Okay. So, no surprise, classical mathematical logic doesn't even recognize that as a problem. If you have a concept, that's your problem. It's not a problem of mathematics. Okay? You need to clarify your mind first before you actually try to use mathematical logic. That's the typical answer you get from a mathematician, which there is a reason for that. Okay? So, but as soon as you move outside mathematics, many problems appear. So that will suggest a possibility. That's what the title of this talk is about. Maybe the logic of mathematics and the logic of everyday thinking, or you can call it the logic of cognition or logic of intelligence, whatever. Maybe they're just different things. Of course, they're related. Okay? Actually, after some study, I'm pretty sure, well, at least to me, they are different things. And also, I can explain where the difference is. That is, the difference actually is in their assumption about the knowledge and the resource the system has or have. Well, concretely speaking, if we analyze from that point of view, we can distinguish different types of systems or reasoning system in general. For example, we can, well, that's my word, my phrase for them. First group, I call them pure axiomatic reasoning system. That's kind of like typical mathematical system, or the thing that mathematicians want to build eventually. That is, with respect to the problem to be solved, the system has sufficient knowledge and resource. By sufficient knowledge, it means everything you need to know is already in the axioms. It's already defined at the very beginning. Okay? What you need to do is actually to derive their implications to reveal the hidden meaning embedded in axioms. As far as resource are concerned, well, as far as a proof take finite step, that's good enough. Okay? Whether that finite means 3 steps or 3 minutes, it has nothing to do with the conclusion is true or not. So mathematicians are looking for a kind of perfect solution, which, as far as you give me enough time, I can give you the truth. Okay? which actually works well in math. But when you move outside that, as I said before, you're running into other situations. For example, people have been trying to build all kind of, you'll see, as in my list, semi-axiomatic reasoning system. Meaning that I know that axiomatic system is good, but the reality is too messy for that to be used. Okay? So I'm going to relax my requirement a little bit. I will allow some uncertainty. I will allow some insufficiency here or there, but I don't allow them everywhere. I will still want to be as certain, as accurate as possible. One example, probability theory. Okay? Traditional logic say everything is either true or false. Probability theory say, oh, that's too much. Okay? But we don't really know whether that thing is true or not. But we still know its probability, right? Or we're supposed to know, or we try to figure out this probability. So the problem is, what if you don't even know the probability? Then you're moving outside the scope of that semi-axiomatic reasoning system. Okay? So then, in this continuum, if you go to the extreme, then this position, that's what I call non-axiomatic. Which means that now, what if we assume in general the knowledge and resource are in general insufficient with respect to the problem to be solved? What does that mean? That means that for the problem to be solved, there are all kinds of things you don't know. Okay? What you think you know, you're never absolutely sure. And you never have the time to actually try all possibilities. Okay? You have to ignore some relevant knowledge, even though you know they're relevant. You don't have the time to think about it. If you have to survive in that environment, what's the best strategy? Or is there a good strategy, or everything is equally bad in that situation? Well, that's my system is trying to help. Now, as you can guess, my system is called Nars, for non-axiomatic reasoning system. So I'm taking that extreme position. Okay? So it's fully based on the assumption that the system has insufficient nonlinear resources. What does that mean? The system has finite processing power, a certain amount of memory. Okay? How much that amount is, it doesn't really matter too much. Okay? It just, as far as fixed. Fixed amount of memory and fixed processing power in terms of number of processors and speed. Okay. And it has to make reaction in real time. It cannot say that I will take 3 hours for this problem, and no matter what, I'm going to spend 3 hours. No. Okay. Also, it must open to all kinds of new information. For example, what if you get new information which is inconsistent with your current belief? Well, the system must be able to deal with that. What if you get a question which is beyond your current knowledge scope? You cannot simply say, I don't know. You are forced to make a guess. Okay? Then in that situation, what the system can do? Well, clearly the system cannot guarantee the correctness or optimum of its solution. By definition, it cannot. If it can, then it actually have sufficient knowledge and resource. But the system can still be adaptive, meaning that I'm trying my best, and also I'm learning from my experience. Okay? That's what the system should do. And guess what? As soon as you take that position, you will see it changes everything. All the previous theory, no matter how good they are, they cannot be applied in this situation anymore because they're making the opposite assumption from the very beginning. Okay? So I'm going to quickly go through the technical points. Okay? Given the nature of this work, and also I have insufficient time, right? So we are not going to go into all the details, but I will show you the basic point. Okay? Every reasoning system starts with a formal language, and I'm using a formal language tool. A typical sentence in that language looks like this. What's that supposed to mean? Well, this kind of language is called categorical language. Actually, in the history of logic, it's actually come before first-order predicate calculus. This is the language used by Aristotle. Okay? Every sentence consists of a subject and predicate. Like in this case, you see bird is the subject term, and animal is the predicate term. A term, you can think that as the name of a concept within the system. These two are related together by what I call an inheritance relation, which is a copular. Intuitively, it represents the relation that a bird is a special type of animal, or animal is a general category than bird. Very simple. And the pair of number attached to that sentence is my representation of truth value, which use two real numbers between 0 and 1, a pair of them. Okay? The first number is called frequency, the second number is called confidence. So that's the simplest form of a sentence in my reasoning system, Nars. What does it mean? Now let's talk about semantics. Okay? So the semantics is basically about two central concepts. One is truth, one is meaning. Okay? So I use something I call experience-grounded semantics. You'll see that I already mentioned, according to traditional model-theoretic semantics, whether a sentence is true or not depends on the reality. Okay? So truth value is kind of a match or mismatch between a sentence in a system and a fact in the reality. In my system, no. Truth value is a relation between a sentence and the available evidence the system has. So as a result, to what degree something is true actually depends on how much system know about that thing. So contrary speaking, there are two numbers. The first number's frequency is the proportion of positive evidence among all evidence. Well, of course, that means I need to have a formal definition about what is evidence, what is positive evidence, what is negative evidence. Okay, I do have that, but I'm not going to mention it. So you see the first number is not that controversial. It looks just like probability, right? But you see, probability means the limit of that ratio, right? In my system, I don't take a limit because limit talking about the infinite future, which I have no idea, or my system have no idea. Okay? So that measurement is completely based on what the system already know at that moment. So that's called frequency. The second one is more special compared to traditional theory. It's called confidence, even though mathematically it's very simple. This W is the total amount of evidence. So it's total amount of evidence divided by total amount of evidence plus a constant, a positive constant. Simplified case, we just take that to be 1. What does that mean? It measures how much you know about that thing. Okay, if you know nothing, W equal to 0, confidence reaches minimum value, which is 0, which basically means I have no idea. The more you know, the higher your confidence is. But as far as your amount of evidence is finite, for every real system, it should be finite. You see, the confidence value never reach maximum, which is 1. Okay, you can be as close to 1 as possible, but you can never reach it. What does that mean? That means the system is never absolutely sure about any of its beliefs. Okay? Whenever there's new evidence come, there is always a chance for the system to change its mind on all of its beliefs. It's just a more confident one will be changed less because you already know a lot. Okay, a couple of new examples doesn't mean much, but it's still possible for you to change your mind. And this truth value actually uniformly represents several types of uncertainty, like what we call randomness, fuzziness, and ignorance. How about the other concept? How about the meaning of a term? for example, what bird means to the system. Again, according to traditional logic or traditional semantic theory, bird means a whole bunch of things outside there. Okay, this is just a label of those kind of things. In my system, no. Again, it depends on what the system have learned or have experienced about that concept. So clearly, a direct implication of this definition is when the system is getting more and more experience, the meaning of the concepts of their terms change accordingly. Okay? And that also means meaning is fundamentally subjective to a system. A different system may have different meaning attached to the same word, even though there may be some overlap. It's not arbitrary, okay? But it is subjective. And also it depends on experience, depends on context, and so on. It's not a fixed thing. A word is not just a label of things outside there. So, okay, that's semantic. Then what kind of inference the system can do? Well, again, here the system is more similar to Aristotle's logic than to first-order gradient counters, in the sense that all the major inference rules are syllogistic, meaning that each of them will take two premises. Each premise, as I said before, is a subject-predicate sentence with a truth value attached. Okay? And also there is a further requirement that these two premises must share a common term. In this case, is the M, right? So which is the subject of the first one, the predicate of the second. And because of the transitivity of this inheritance relation, you'll see that you can have a conclusion which link the other two terms which are not shared in the premise. This is the same as in Aristotle's logic. But Aristotle's logic is still binary logic. Okay? This one clearly is not. So the truth value of the conclusion will be calculated from the truth value of the premises according to a truth value function. Okay? Which in this case, this is the deduction rule. The truth value function very simple, looks like that. Why? Again, I have an explanation in my publications, which we don't have the time to talk about here. Okay. So intuitively or graphically, you see it's very simple. It's kind of like you can take each node as each term as a node, and each statement as a link, then a direct link in this case. And this transitivity means if you have a link here, you have a link here, you can build a link here. And all the links are weighted by this pair of numbers attached to it. Okay. So deduction is nothing but an extended version of transitivity of this inheritance relation. Okay. It's just now it's not binary anymore, it's a matter of degree. So we can see a concrete example. So if you believe birds, or the system believes birds are animals to a certain degree, and also robins are birds, and then it derives robins animals. This one, I guess, is not controversial at all. It's just like, you know, almost every AI reasoning system, as far as it can handle uncertainty, will have something like this. Okay? It just, I use two numbers which looks weird. And here, actually, you don't see why that's needed. But the next rule will change that. Induction. You'll see the overall pattern looks like before, but if you pay close attention, you will see. Now the common term is the subject of both statements. Okay, so that graphically speaking is something like this. You have link here, you have link here, then you try to build a link here. Many of you will say, "Oh no, there is also a semantic link." Yes, there is. Okay, I've just tried to make things simple and then mention that. And also the truth value function looks different. Again, we don't talk about the detail. Let's see the example. What the example say? Okay, the example say that the system believes to a certain degree, which I use that 1 for frequency, 0.9 for confidence as a default. Just say that that's a normal belief to that degree. Okay. This 1 basically means all the evidence are positive. This 0.9 means that I have a certain amount. So if the system believes swans are birds, and swans are swimmers or can swim, then it will derive a conclusion and say birds can swim. Well, if we don't look at that truth value attached, that's a typical fallacy. You can find in every logic book tell you that's wrong, you cannot say that. But that's what the problem about induction is. You try to generalize from your observation. Okay? You only observe the one concrete example of bird, which is swan. Now you know that thing swim. Now you generalize to a bird in general. You say, I guess bird maybe be able to swim in general. Do you know that? You don't. You don't fully, but you know something about it. That is, we can take swan as a piece of evidence for the conclusion. That's exactly what this conclusion says. This truth value. Okay? Frequency is 100 because according to the given evidence provided by the premises. Well, here you see I'm assuming the system knows nothing else. But the evidence directly presented in the evidence, in the premises. Okay, if that's the only thing you know one thing, which is a bird, no matter what it's called, and that thing can swim. Okay, that gives you positive evidence for a bird to be able to swim in general. However, you cannot say that's completely true. Of course, it's not. Okay, so that's what this confidence value is about. And this 0.45 actually measures how much evidence you have collected for the conclusion. In this case, it's just the one that's provided by Swan. Okay. If you compare this rule with the previous deduction rule, you will see that induction rule, the confidence level in general are much lower than the deduction rules. Why? Because it's only based on one piece of evidence. But you still have something. It's not complete. It's not either you know everything or you know nothing. Okay, that's what traditional logic is doing. And this logic try to fit in between, say that I don't know everything, but I know at least I know something. Okay? So symmetrically is the abduction rule. Here you see the common term is the predicate of the total premise. So you have a link here, you have a link here. Then you try to build something here, and of course, the other way around. Okay? So what that means? That basically means you see, intuitively speaking, a subject is an instance, a predicate is a property. So what we have here is two things have a common property. So because of that, okay, the system gets, if we know seabirds can swim in general, and gal we know can swim, from that information alone, okay, the system gets, I think gal is a kind of seabird before anything else are taken into consideration. So you'll see in this system what we call hypothesis or guess on one hand, and what we call a fact and reality or truth on the other hand, it's continuous. Okay, it's just a matter of degree. What we call hypotheses are the things that we have low confidence, which is typically produced directly by non-deductive inference. On the other hand, deductive inference typically gives us high confidence conclusions. But even if that's the case, then how can you get high conclusion generalization or in this situation in your explanations? Well, even if we don't use deduction, even if we do abduction or induction alone, you can still get high confidence by seeing more and more and more and more and more, right? So in the previous situation, if you see another bird which also swims, which make you believe a little bit stronger on bird swim. The same thing here, if you check another property of seabird, which is also a property of gull, then you believe more that on the conclusion. So that thing is handled by the revision rule. It's kind of like you have two things, two conclusions about the same thing, but from different sources. Okay, now you combine them together, by pulling the evidence together, you get a stronger conclusion. How you see that? Well, this truth value function looks complicated, but in reality, another form is actually very simple. That's basically say that the positive evidence for a premise will also be a positive evidence for the conclusion, and negative evidence for the premise will also be a negative conclusion, negative evidence for the conclusion. Okay, then you use the relationship between conclusion, evidence and the truth value to get this formula which looks complicated. Intuitively speaking, you see the frequency part is just a weighted average of the two in the premise. Okay? Like here, for example, you have positive evidence for bird to be swimmer from one source, but negative evidence for bird to be swimmer from another source. Then you combine them together, you get something in between, but not right in between, because the first premise is stronger in terms of confidence value. So it's kind of like more that position. But if you check the confidence value, you'll see this confidence value is higher than either this one or this one. Why? Because this is a summary, right? So you summarize the thing together, and the confidence is only about the total amount. So that the more you get, the more confident you will be, no matter whether it's positive or negative. So you'll see that's the basic rule of the system at the core. Then also now you can see that what is the memory value, intuitively speaking, is just a weighted directed graph, right? With nodes for terms, links for statements, the truth value will be the weight attached to that. Also what we call a concept, you see here, is nothing but all the links that coming into or going out of a given node. Or in other words, that's whatever the system knows about that thing. In this case, it's about the concept of bird. So when the system is running, the control strategy goes like this. From the previous slides, you know that the memory is basically a directed graph. So when the system runs, what it does is repeat an inference cycle which pick a node in that network or in that graph and pick two links from that graph and try to make an inference. Okay? And each of the links will represent a task the system will try to process. At this stage, a task will either be a piece of new knowledge or a question the system needs to answer. And what the system does is it's going to use a belief within the same concept, and that belief represents knowledge the system already has. Then what rules is applicable is completely determined by the task and the belief. So those rules will produce new tasks will be added into the network. So now we see that the key of the control strategy actually is in the selection of the concept, the task, and the belief. Well, instead of following a predetermined algorithm, what the system does is to give each of them a chance, but a different chance. So the selection carried out probabilistically, meaning that there is a priority value defined among the concepts and tasks and beliefs, and high priority means a higher chance to be accessed or to be processed. So now people will ask, okay, in that case, how can you decide the priority? Okay. That's a long story, and in general, a priority depends on several factors. For example, the quality of a data item. For example, if you have two statements about the same thing, and one have a higher confidence value, the other one have a lower one, everything else about the same, then the high confidence statement should have a higher priority because it's more reliable. Another factor is the usefulness of an item in the history of the system. So if a concept has been very helpful in solving a certain type of question, then it should be used more often in the future in similar situations. And also, the relevance of item should also be taken into consideration. For example, when the system is working on a problem, the concepts that directly related to that problem should be given more higher priority. So here it's kind of like activation spreading in neural net. So this is basically how the system works in a highly simplified version. But of course, to really make this thing to solve the AGI problem, what I just said is far from enough. So there are many other things in the system which I will only briefly mention without going into detail. First, for example, the terms in a statement. It is not necessarily just a simple word. Okay? It can be a compound, just like in natural language. When we analyze a sentence, we say there is a subject and predicate, but usually they're not words, but phrases, okay, with words in them. So you'll see here we have different ways to make compound term, which will serve as subject and predicate. And also, inheritance is only one of the possible copulars that can be used to link terms into a statement. We have other types of copulars. And also, besides the rules I mentioned, there are a whole bunch of other rules which will do other type of inference. And also, the memory and control structure, the reality is much more complicated than the one I just mentioned, even though the basic idea is here. So based on this, we have another layer of the system which is called higher order reasoning. It's because here the basic idea is we can treat statement as a term, so that we can have statements about statements about statements. And we can build relations among them. We can build compound structures upon them. And this kind of thing can be used for many types of inference, for example, conditional, hypothetical inference. And also we can introduce variable terms which can be used as symbols of other terms, so that we can use that for general and abstract inference, like in mathematics. And finally, on top of that, we can further extend the concept of reasoning by treating other things as statements. For example, in the system, events are treated as statements with temporal relations, so that an event is just a statement with a truth value which only hold for a certain period of time. Okay? Then based on that, we can say that this event happened after that event or before another event. Or we can say these two events happened at the same time, things like that. So that there's a special type of inference, for example, temporal inference, that can be used for prediction, so that you can use the current situation as a base to predict what will happen next. Then another type of special statement, operations, which is an event, but the difference is a typical event is something from an observer's point of view, but an operation is something that the system can actually do something to make it true, or is something executable. So with that, we can actually make the system run, and also at the same time to change part of the environment and itself. And furthermore, those operations can be combined together to get compound operations, more complicated operations, which in psychology will be called skill learning. In AI, it will be called, for example, reasoning, planning, or self-programming. Okay, so that the system, when it's getting more and more complicated experience, in the long run, it should be able to build a complicated skill from some very basic operations. And finally, we have some goals in a system which can be handled as statements to be realized. Okay? So just like a common statement is just saying that this and this is true. Okay, a goal is kind of more like I want that to be true. Okay, what can I do to make it true? So in this way, goals can be handled by reasoning systems, so you can reason about goals. And finally, you can do decision making to decide whether to actually pursue a certain goal or not. This kind of reasoning is necessary because when you have a complicated situation, you may have multiple goals which are not necessarily consistent among themselves. Okay? So you may think, well, you may want to do this operation for this goal, but at the same time, it will damage some other goal. So if all of the things need to be taken into consideration, then whether you need to execute or take a certain operation or not. Okay? That need to be handled by this type of influence. So in summary, I guess today I actually raised more questions than I answered. And because of the claim I'm making and the supporting evidence I'm providing doesn't really match each other. But again, I have an excuse, right? Insufficient resources. So, but I hope you can believe, well, you don't have to believe me, but that's the thing that you may want to think about, at least. Okay? So, one conclusion is, even though my system is not fully finished yet, okay, otherwise you should have heard about it, right? It's possible to build a reasoning system that adapt to its environment and work with insufficient knowledge resources. It's possible to do that. It's not like at the very beginning, many people will say, yeah, if you want to make a logic, you have to assume something is absolutely true. Otherwise, it's not a logic. That's wrong. Okay? You can still build something which is fully formalized, but without that assumption. It's possible. And the second one is, if you actually do that, you will see that many of the questions in AI and cognitive science are solved all together. You don't have to solve this one, this one, this one, this one. Okay, why? Because to a large extent they come from the same root. If you solve the problem there, everything else, or many of them, will follow. Thank you very much.
We would like to open the floor for questions for at least 10 minutes or so for those of you who want to ask Pei questions. So please go ahead. Yeah.
So do you have implementation in the system?
Yes, I do. It's not everything, but at least the part I covered today, all implemented. If you go to this website, I actually have an online demo, and also all the source code are open source. So you can see the source code, you can run the demo as a Java application, Java applet. Even though that I haven't solved any big practical problem yet. All the examples there are very simple examples, just show you that step by step what the system can do.
But are there even some like path problems that you've shown that you're able to solve more efficiently,
Yes.
or that you couldn't do with more traditional?
No, at least my examples, even though they are simple, I can say that no other system can get that result. For example, by data-driven way to combine deduction, induction, abduction, and analogy in the whole sequence without telling the system, what to do at each step.
Yeah, I think you're right. Like induction is very important if you're trying to mimic like the
Yes.
human-like reasoning. But I'm not convinced necessarily that this is the way the human do the induction.
No, this is not supposed to be a psychological model. So I'm not trying to stimulate the detail of human thinking. Instead, I still try it's a logic I still try to kind of be abstract. I just say that my assumption is more realistic compared to other logic.
Yes, but in the end, you would also like to get more like a human like reasoning out of it, right? Because then you would have a system that could...
Yes, it's just a matter of degree.
Yeah.
I think my result will match psychological data better than classical logic, but it will not match human thinking perfectly.
Yeah, that's right. And you don't necessarily want that.
Yes.
You're not trying to mimic the way the human does, but you want to, you're just trying to achieve more human-like.
Yes, human-like
behavior.
That's the word. Yes.
Yeah, so it would be interesting to actually get some more hands-on. I'll visit your page.
You're welcome to visit my website. I'm not really trying to convince anyone today, just because this is such a big topic.
Yeah, but in the end, somehow you need to evaluate this, right?
Yes.
How well you achieved, and that's always a
Yes,
big problem.
that's
and you don't
actually
have
a big issue. Yeah, because you see, you cannot evaluate this according to a traditional theory,
exactly.
because it's based on different things. On the other hand, you cannot evaluate pure empirically against the human data because it's not supposed to be a descriptive model.
Yes.
So my position is kind of like in between. I just say that the assumption I'm making can be evaluated empirically. That is, I believe human beings are adaptive. Human mind actually works with insufficient knowledge and resource. Okay? That thing I think can be checked in empirical way.
So I think it would be interesting if the artificial intelligence, general intelligence community would have some kind of a benchmark problems.
We have been talking about this, for many years. In the past years.
Yeah, because that's the only way to test different approaches, right?
Yes, but it's very difficult.
But it's
especially because of the
assumption
people are making. And also another issue on which I didn't mention today is actually there are very different understanding about what intelligence is about.
Yeah.
You see, for me, it's about some general principle of rationality. Some other people say intelligence is just the ability to solve practical problem. Okay, so for those people, they are not going to evaluate their system according to something I like.
Yeah, exactly. But in the end, we need to have some way of evaluating it just as a scientific discipline. And
otherwise we will be in big trouble. How can you claim?
Exactly. And we cannot go about it right. We have to wait until we solve the entire problem to be able to test.
Exactly. We don't know the solution.
We need smaller steps on the way.
Yeah.
All right, Eric, you had a question?
Yeah. If we go back to the definition of frequency and confidence, it seems to me at first sight that this will bring some inertia to the sentence. For example, if something has accumulated a lot of evidence, the plus is big, W itself is extremely big. Then we change slightly the condition. What used to be true in this room, in that room is not true anymore. It will take a long time to figure out that this model is wrong in this context.
Yes.
So what is your take on this?
My take is for that kind of thing, you really need the thing I mentioned in the last level, self-control. You need to consciously say, that piece of evidence doesn't apply to this situation anymore, so I'm going to recount, and I'm going to exclude them.
Okay.
So, but what I show is just like kind of naive, direct accumulation, which clearly doesn't handle that. Okay? If, for example, at a certain moment you know that some guy you have trust in the past have been telling you all the lies, of course you need to calculate your confidence value on many things. Yeah, that's not covered by that component.
But if the system gets a contrary evidence to assumption it's making, does it nullify its confidence in the assumption, or does it just lower the probability?
If in general, if you don't really have that kind of thing I already just mentioned, you just have evidence from different sources. Now you don't have any reason to challenge the reliability of those sources. If that's the case, the confidence always goes up. You're knowing more and more and more and more. Frequency can either go up or down, depending on whether those things are positive or negative.
Are the sources, do they have different values according to what the system looks as more important than what it looks as trivial?
In the current stage, importance doesn't really matter in that calculation because all evidence will be taken kind of like on the surface level. But yeah, in more complicated situation, you can use your self-control. Say that for this judgment, for example, I only listen to the opinion of a couple of sources. I purposely ignore the others. You can do that. But that's, yeah, more complicated version of this.
Instead of making this computer, learn everything, couldn't you make it, just use the information that is already known?
Oh, of course, of course.
Maybe take all the facts from the internet or something.
Yeah, that's actually the plan. Because here we are only talking about experience, but this experience can either be direct personal experience to the physical world, or like many of us, is more indirect experience from other human beings or other systems. So in reality, yes, most of the resource knowledge will come from the internet. But it's just the system's personal experience will also matter. It will be combined together.
Anna?
So I'm not quite sure I understood how the deduction is performed, but does it compare with knowledge-based probabilistic logics or belief logics with updates or trust models? They all have this kind of reason.
Yes, to different degree. I already have several publications, for example, to compare this with Bayes network.
Yeah.
Bayes network is also, everything is true to a degree. And also I have paper to compare this system with, for example, fuzzy logic, which is, say, truth is a matter of degree, the same thing. Again, if I say, in summary, the major difference, again, go back to my assumption of insufficient knowledge or resource. For example, in probability theory-based system, they say everything is a matter of degree, but at least they insist all the probability values are consistent with each other.
Belief models don't.
Belief model don't. If by belief model you mean Dempster-Sheffer theory?
I don't know that well
Okay.
about it, but I still know that there are conflicting.
My system is similar to many things in my solution list here or there, but not identical to any of them. Just basically because, you see, they typically say, we allow uncertainty here, but we don't allow uncertainty here. I typically say, I allow uncertainty everywhere. For example, also non-monotonic logic, okay, which allow the system to change its mind, just like mine. But in that system, it assumes, you can change your conclusion, but you cannot change the default rule, which is fixed. I say that I not only allow to change the conclusion, but also I can change the default rule if I get enough negative evidence. Like, for example, bird flies. That's a typical example used in default logic. Okay. So that they basically say a bird typically flies, and they know this can be wrong. So you get a bird which is hurt or too young and cannot fly. But they say bird flies cannot be changed by experience. But in my system, you see, even if I tell it at the very beginning, bird flies in general, if I begin to run millions of birds, none of them can fly. It will change by default. Okay? So that's why I call it non-axiomatic logic in a sense that no concrete knowledge is axiom or absolutely true. Everything can be changed. I guess most of the other system doesn't go that far. They come to say, this part can be changed. This part is fixed. So that's a general conclusion. But if you're interested in a detailed comparison between this one and another logic, we can talk about that afterwards.
Okay, I think we'll conclude this here. Thank you very much for coming, and let's thank you.